again say when sigma is equal to 0, so the poles will be occurring on the unit, not on the unit circle, on the 0 axis, or j omega equals 0 axis. So first we considered our pole in the left hand plane. Now we are considering it on the 0 axis, and in that case r will be equal to E minus sigma. At this point sigma equals 0, so 0, and r will be equal to 1. So in that case the poles will be mapped on the unit circle. So this is our new mapping. And many of you have guessed, when sigma is greater than 0, r will be e raised to sigma t, r will be greater than 1, and in that case the pole will occur in the right hand plane, and the pole will be found outside the unit circle. So this is our 3 different mapping for the impulse invariance technique. Needless to say, if sigma is greater than 1, or if we set our condition as such, the filter that will be designed will be unstable in nature. Okay, now let's move on and look at a mathematical problem on solving IIR filter using impulse invariance technique. Okay, so the example is, the problem statement is for the analog transfer function h of s is equal to 1 over s plus 1 and s plus 2. Determine h of z using impulse invariance method, and assume the sampling frequency f of s to be 5 samples per second. So let us go to the solution. So once again, let me remind you of our task. First, we are given with an analog transfer function by the virtue of inverse Laplace transform. From there we will get HA of t in the time domain, or you can write h of t. Then by the virtue of sampling we will get HNTS, and finally from there we will get h of z by the process of z transform. Now here the given transfer function is h of s is equal to 1 over s plus 1 and s plus 2. Now in order to operate the inverse Laplace transform, first what we need to do is divide it into 2 different fractions, or rather as the summation of 2 different fractions. This can be done using the renowned technique of partial fraction. So this can be considered a over s plus 1 plus b over s plus 2. Now in order to determine a, we will simply write a will be equal to the denominator of a, s plus 1 times h of s, where our s will be equal to the negative constant value in the denominator of b. So if this is s plus 2, s will be equal to minus 2. So solving s plus 1 and h of s is equal to 1 over s plus 1, s plus 2, this will be not be equal to the denominator, rather it will be the negative value of the denominator of h of a, so this will be s equal to minus 1, so s will be equal to minus 1, so this 2 will cancel out, put s equal to minus 1, so 1 minus 1 plus 2 will be equal to 1. This is a, and similarly for b we can write the denominator of b is plus 2 times h of s, where s will be equal to the negative value of the constant term, that is minus 2. So once again s plus 2 times 1 over s plus 1 times s plus 2, just putting in the value of h of s. S will be equal to negative of 2. This 2 will cancel each other out, and we are left with minus 2 plus 1, so this will be equal to minus 1. So finally we can write h of s to be equal to 1 over s plus 1 minus 1 over s plus 2. Now we go on to our step 1, that is applying the inverse Laplace transform. So h of s will become h of t, and this will become Laplace inverse 1 over s plus 1 minus Laplace inverse 1 over s plus 2, and using the previous formula we can write this to be e raised to minus tu of t minus e raised to minus 2t u of t. So we can write h of t to be equal to, just take u of t as a common factor, so e raised to minus t minus e raised to minus 2t u of t. This is our first step done, that is the inverse Laplace transform. Now in the second step what we do is sampling. So in order to sample the values, just replace t with nts, where ts can be written as 1 over fs, and fs in our given example is equal to 5 sample per second, so this can be written as n over 5. So plug in this value in the expression of h of t, so h of n by 5 equal to e of, okay, first of all let me keep it as nts, so this would be minus nts e raised to 2nts u of nts. So now the second step is also done. The third step will be applying Z transform. So applying Z transform, we get h of z to be equal to summation where n goes from 0 to infinity n goes from minus infinity to infinity h of nts z inverse n. Putting in the value of h of nts, we get summation where n goes from 0 to infinity e raised to minus nts e raised to minus 2nts times z inverse n. The limit is changed obviously due to the multiplication with the unit step. So we can write h of z to be equal to, just decompose this two exponents into two different summations. So the first one will be n goes from 0 to infinity e raised to minus nts z inverse n minus summation n goes from 0 to infinity e raised to minus 2nts z inverse n. This can be further written as summation where n goes from 0 to infinity e raised to minus ts z inverse whole raised to the n minus n goes from 0 to infinity e raised to minus 2ts z raised to minus 1 whole raised to n. This expression is in the form, once again, is summation a raised to n where n goes from 0 to infinity, which will be equal to 1 by 1 minus a. So both the summations are in this form, so this can be simplified to 1 over 1 minus e raised to the minus ts z raised to the minus 1 minus 1 over 1 minus e raised to the minus twice ts and z raised to the minus 1. So, and now moving on, what we will do, so we got h of z to be equal to 1 over 1 minus e raised to minus ts z raised to minus 1 minus 1 over 1 minus e raised to minus 2ts z raised to minus 1. First of all, we are going to add or subtract these two terms up. This will be minus e raised to minus ts z raised to minus 1 minus e raised to minus 2ts z raised to minus 1 z inverse e raised to minus ts e raised to minus 2ts. So this is the summation, the subtraction of the fraction. Now we can write ts to be equal to 1 over fs, which is equal to 1 over 5, which is equal to 0.2 seconds. And replacing the value in this expression, we get h of z to be equal to z inverse e raised to negative of 0.2 to negative of 0.4 1 minus e raised to negative 0.2 z inverse minus e raised to negative 0.4 z inverse. And finally, we need to take the expression in the form of 0.148 z squared z. Now, to get from this line to this line, just multiply these two factors and divide the, and multiply the numerator and the denominator with the highest power there is, and you will get to this form. And these values are easily calculated through the use of calculator. So this will be our required expression for the impulse invariance method. It could not be stressed more that you go from this form to this form in your examination. This is the final form of the result. If you keep it up to this point, you might not even get the complete marks. So with that, we come to the end of our discussion of impulse invariance method. In the next video, we shall be studying design of IIR filter using bilinear transformation.